Okay, welcome back. We will just again start from where we left last time. We have introduced the another new type of strain to you while discussing the conformation of cyclic systems, and we have seen that these molecules, especially the small membered rings, they suffer from a strain which is called the angle strain. Now, according to modern day theory, because if you look at again I show the cyclopropane ring, you see the bonds are, I had to struggle to connect these two hands. Okay. It is so much bent and the model is almost coming apart, ruptured at this point. So, the question is whether the molecule really looks like this or not, or there is some alternative way of thinking the conformation of cyclopropane. Okay. Now, according to the modern day theory, when you draw the orbitals, so you have the sp3 orbitals of the carbon, and this angle is, we know it is 9.5 degrees. Now, if you write another carbon here to make another say 2 carbons here to make the cyclopropane. So, what is happening now? This orbital is pointing towards this direction, see, and this orbital, let us just concentrate on these 2 carbons, the connection of this carbon with that carbon. So, what happens? These orbitals are no longer pointing towards each other, in a head on fashion, means in a linear fashion, which forms the strongest sigma bond. So, in a sigma bond, the orbitals should approach in a linear fashion, okay, in a coaxial fashion, and so that the overlap is maximum when they come close to each other. So, there will be overlap of the orbitals. This is the overlap portion. The extent of overlap will determine the strength of the bond. In case of cyclopropane, what happens? As these carbons come closer, the orbitals are no longer approaching in a linear fashion. So, this is one orbital, and this carbon, the orbital will be like this, and for this so another carbon is here. So, here also very similar situation, this is pointing towards that direction, this is pointing towards this direction, and for this also. So, in no case the orbitals are, unlike in a real sigma bonding situation scenario, the carbon atoms are no longer have the orbitals pointing towards each other in a linear fashion or in a head on fashion. So, if you do that, that means they actually approach in an angular way. In sigma bond, they should approach in a linear fashion. In pi bond, we know that they approach in a lateral fashion. So, this leads to sigma bond and this leads to pi bond, and we know that the pi bonds are less stable than the sigma bond, simply because the extent of overlap is much more here rather than the extent of overlap if they approach laterally. And this is a scenario which is in between this. They are not lateral, they are not head on also. So, what happens? They actually approach in an angular fashion. So, this is the angular fashion, that is what I am saying. So, the extent of overlap now will be less. If the 2 carbons approach head on, then the amount of overlap that you get between the orbitals, that will be much more. Here the extent of overlap will be less. This is the extent of overlap, this is the extent of overlap. Okay. So, another way to look at this system cyclopropane is to tell that the bonds, see, when they join each other, when these orbitals combine with each other in phase, the orbitals are in phase, then ultimately the molecular orbital that will be generated, they will look like they will look like this. Now, these are what are called, so you see the bonds, but these are now orbitals, these are no longer very mechanical concept of bonds, this is the orbital concept. So, they will look like, these are called banana bonds or bent bonds. Okay. You can call it as bent bonds, the bonds will be bent, or you can say that this looks like a banana. The overlap, ultimately the molecular orbital that is generated, that looks like a banana. So, that is called a banana bond. And this banana bond will be much weaker than a carbon-carbon single bond in a linear alkane, because as I said, because they do not approach in a linear fashion, they approach in an angular fashion, and that is why the extent of overlap will be much less. So, this is the molecular orbital concept of instability of cyclopropane. So, what is the answer? If somebody asks you, according to Bayer strain, you say that they suffer from angle strain, but the real picture, because molecular orbital theory came much later, and this is the accepted version of to explain the structure of molecules. So, what happens in the molecular orbital theory, according to that, the extent of overlap that forms the carbon-carbon bond in cyclopropane is much less, because the orbitals approach in an angular fashion, and that makes the bonds are no longer perfect sigma bonds. So, it is in between a sigma and a pi. It is not a pi, because they are not approaching in a lateral fashion. It is not a perfect sigma. It is a sigma bond, but it will be much weaker than a sigma, than normal sigma bond. And how do you know it is weaker? Because you can do many reactions on cyclopropane, which is looking like as if it is possessing a double bond. Like in ethylene, if you add HBr, we know that the bromine adds Cr and H adds Cr, whereas in ethane nothing happens. If you add HBr, it does not break, that one side bromine goes, another side hydrogen goes, because this is a very strong bond, you cannot break this bond. Okay. But this happens with with ethylene, because the pi bond is very weak. Similar things happen with cyclopropane. So, if you take cyclopropane and add HBr, so as if this bond is like a pi bond, is a weak bond. So, on one side bromine is added and the other side hydrogen is added. The difference between this and that this is a 1,2 addition and that is a 1,3 addition. Okay. But the similarity is there, that this bond is weak and you can break and there will be a 1,3 addition. It is an addition reaction. Okay. Similarly, if you add hydrogen in presence of a catalyst, then you will get the normal propane. If you add bromine, you will get 1,3 dibromo propane. Okay. So, that shows that these bonds are weaker. Okay. Now, there is so that is the how it is described, this banana bond. Now, there is another concept that also that came up little later, once the banana bond was that theory was put forward. Then people started looking at this molecule again, and people calculated, you can calculate that what will be the strength of these bonds, if they are perfect, these perfect banana bonds, and if the carbon is sp3 hybridized, then what will be the extent of overlap, you can calculate that. So, this bond strength can be calculated. Okay. And during the calculation, what they found, that cyclopropane bonds, as per calculation, the whatever be the strength, means as per the overlap, if you whatever the strength comes out, actually the strength of the carbon-carbon bond is slightly higher than that. Means as per calculation, quantum mechanical, these calculations, this orbital overlap, you can calculate. So, as per calculation, you get a bond strength, suppose x kilocalorie, suppose per mole, and actually you can also by combustion experiments, you can or by hydrogenation, you can tell what is the strength of this carbon-carbon bond, and suppose this is Y, kilocalorie per mole. So, what they found that actually Y is little larger than X. So, where was the problem? Because this should match, then there is something problem with this calculation, but quantum mechanics is based on a sound footing. So, that you cannot challenge, it is very difficult to challenge that concept. So, something extra must be happening to this molecule, so that the carbon-carbon bond is slightly more stable than what is expected out of calculation from molecular orbital theory. So, then it was revised a little bit. This is the modern day concept of cyclopropane, that you know that if a carbon is sp3 hybridized, then the bond angle becomes 109 degree, 109.5 degrees. If it is sp2 hybridized, then it is 120 degree, the bond angle, and if it is sp hybridized, the angle becomes 180 degree. So, what does it tell? That as the percentage of, so the percentage of p character is highest here. Okay. So, the percentage of p character, as it p character, percentage of p character in the hybrid orbital, so if the percentage of p character goes down, so p character is increasing on this side. So, this is 50% p character, 50% s character. Here it is 1/3, that means this is 33 point, this is sp2. So, s has 33.33. So, this is about 67% p character, I am talking about p character, and this is 75% p character. So, as the p character increases, the bond angle decreases. Okay. As the p character increases, the bond angle decreases. So, with this presumption now, the modern day theory is that this carbon is no longer perfectly sp3 hybridized. See, what was the concept of hybridization? The concept of hybridization was that you take orbitals and orbitals of different energies, some may be same energy, but at least one has to be different, like sp3, 3 p orbitals of same energy and 1 s of different energy. You mix them and you generate, because 4 orbitals are combining, you generate 4 new orbitals, which are called hybrid orbitals, and the extent of these hybrid orbitals have all of identical energy, okay, identical energy, that is the important thing, and that means they are degenerate. So, you generate a set of degenerate orbitals, and the percentage of the character, the s character in all the 4 orbitals, like this is one orbital, hybrid orbital, this is another hybrid orbital. So, there will be here, there will be one hybrid orbital, there will be hybrid orbital. So, this is the sp3 situation, okay. And the percentage of s character or p character will be same in all these 4 orbitals. So, that was the concept earlier. Now, in case of cyclopropane, once they found that actually this bond is little bit more stable than what is coming out of calculation. So, they revised this hybridization concept a little bit. So, what people are saying that the percentage of, we know that as the percentage of p character goes up, the angle decreases. Okay. So, if the percentage of p character goes above 75%, then the angle will further decrease, and if the angle further decreases, then according to Bayer-Strain theory, see there is angle strain here, the normal angle should be 109 degree, 109.5 degree, but if you think it is as a rigid system, it is 60 degree. Okay. And in terms of molecular orbital theory, there is less overlap if they approach this as per the hybridization concept. Okay. Now, if you increase the percentage of p character here in this orbital and percentage of p character in this orbital, then what will happen? This angle, what you are seeing here, that angle will further will decrease, because you are increasing the percentage of p character in these orbitals. You can also see it, you can also explain it in here. If this bond, the normal valency angle is 109.5, keeping the p character as 75%, but if the p character say goes up to 90%, then what happens? This angle will no longer be 109.5. So, the angle, suppose the angle what is required in a hybridization, say SP5 hybridization. Now, we have never heard of SP5, but SP5, if it is SP5 hybridization, then the angle will be less than 109.5. I do not know what will be the angle, suppose this is 100 degree. Then the effect of that, the overall angle strain, which was earlier 49.5 divided by 2, that means 24.75, that will be less now, because now you have to have 100 minus 60 divided by 2. So, that becomes 20. So, the angle strain decreases. So, now this carbon is intelligent. Once it sees that there is a problem, if I have a perfect equality amongst the hybrid orbitals, so it will, what it will do? It will put more p character in the bonds which are making the cyclic system, and but you have to compensate that. If you put more p character here, so you will have to have a less p character on the outer bonds which are outside the ring, which are not making the ring bonds. So, the bonds which are not making the ring bonds, you make more s character or less p character here, and here you introduce more p character. And now, the rough calculation, people have calculated that what is the extent of hybridization on this side and what is the extent of hybridization on this side. They found that this can be explained, this inequality of bond strength can be explained if you think that this carbon is sp5 hybridization on this side and the rest is outside. That means, the rest, the outside bonds, again I repeat, they have less p character, this has more p character, and the p character is about what is required, what is present in sp5. So, that will be about what 5 by 6 into 100%. So, the percentage of p character in the inside bonds will be 5 by 6 into 100. So, that comes around 500 by 6, that means 8, 20. So, around 83%. So, around 83% p character in the inside bonds. Okay. That explains so many things, because if you increase the p character, the difference, the bond becomes little bit stronger, because now they approach in a more linear fashion. It's not linear exactly, but earlier the extent of overlap what was there as per sp3 hybridization, now the extent of overlap will be more. So, this bond becomes stronger, now it matches with the whatever is the experimental value. It also matches with the reactivity of cyclopropane, because as the p character increases, the bond becomes weak, because the s electrons are closer to the nucleus. So, greater the s character, the bond becomes stronger. So, these bonds become weaker, and these bonds in turn should become stronger. That means, in cyclopropane, the CH bonds become stronger compared with a linear system, and the CC bonds become weaker, because this has got more p character and this has got more s character as present in a linear system. So, this has got more s character. Okay. So, today you have learned that hybridization does not always follow democratic rules that everything has to be equal. Okay. So, there is inequality in hybridization also, especially when it is required. Okay. So, that is well explained in case of cyclopropane. And the question is, what is the proof? Is there any real experimental proof that yes, there is the outside bonds in a cyclic system like cyclopropane is stronger? So, people have done this. So, they made, this is what is called cyclopropanone. So, they put a ketone here. Okay. Now, this molecule will suffer from more angle strain because this is now sp2. So, this is 120 degree as per normal hybridization, but actually this is required as per hybridization, but actually the angle is 60 degree because this is a 3-membered ring. Okay. So, it will suffer from more angle strain. So, again what will happen? The percentage of p character here in these two bonds will be increased, so that the angle strain is minimized, or the other way the bond strength is more, so that the overlap is more when the orbitals approach each other, So, there will be more p character here. So, there will be more s character on these bonds. So, this carbonyl should be stronger than if you take a cyclobutanone, or forget about cyclic system. This carbonyl should be stronger than acetone, because in acetone there is no such strain, there is no such problem, the angle is perfectly maintained. So, this will have more S character, and this will have less S character. So, which carbonyl is then stronger? Because as I say, the S electrons are closer. So, this carbonyl is stronger than this carbonyl. That you can measure. There are spectroscopic ways to measure that what is the energy required to stretch this carbonyl bond. That if you want to stretch the carbonyl bond, you require more energy for this than that. And this is what is measured in what is spectroscopy called IR spectroscopy. And people have shown that the IR spectroscopy gives the stretching frequency that is required. That means, the energy, the frequency corresponding to the energy which is required to stretch this bond versus to stretch this bond. And it was now perfectly, it is established that this requires more energy to stretch than this one. And so, also if you come to cyclobutane, so it will be easier to stretch compared to cyclopropanone. Cyclobutanone carbonyl will be easier to stretch than in case of cyclopropanone. Okay. So, that is the modern day. First I said that there is this existence of what is called a banana bond, that the orbitals are approaching in an angular fashion. So, that creates what is called banana bond, and then I said that to further aid the strength of the bond, to further reduce the strain that is present in cyclopropane, or to try to strengthen the carbon-carbon bond, there is unequal hybridization. So, what the people said that there is the hybridization, the hybridization are not equal in all the hybrid orbitals. So, some orbitals have more S character and some orbitals have more P character. It is the inward bonds, that means, the bonds which make the ring, those bonds will have more P character, because more P character means less angle, and less angle means less angle strain. Okay. And I can show you here, I think there will be some pictures here for. So, I started with this, that cyclic that we have known what is called torsional strain, what is called steric strain, those are introduced while discussing the acyclic systems. Now, what we have is what is called angle strain, that is what also known as Bayer's angle strain. And if I completely show the slide, this is what is the slide. that in case of cyclopropane, I should have also mentioned this, that there is angle strain, that is true, and there is another strain, that is the what I said, the bond opposition strain, because these two bonds, the sidewise, they are eclipsing each other. So, there is what is called eclipsing strain, or you can call bond opposition strain. So, their dihedral angle is 0. Okay. So, there will be that bond opposition strain that is present here, but the major contributing factor for instability is not this bond opposition strain. This is present definitely, but the major contributor is the less overlap, according to molecular orbital theory, less overlap while forming the carbon-carbon bonds. Okay. And here the picture, it says that it suffers from torsional strain. Torsional strain is the one that when you lie in energy maxima, you will try to go to the minimum point close by. Okay. So, it suffers from this torsional strain. Okay. Torsional strain is absent in case of staggered form, but this is in the eclipse form. So, this will suffer from torsional strain, and this will suffer from another strain, that is what is the angle strain or Bayer strain. And this whatever I said, these are all explained here, that actually the hybridization generally is democratic. That means, the percentage contribution of each orbitals in the hybrid orbital is usually same, but that does not happen in cyclopropane. Before that, people said that there is this type of bond. I told you about the banana bond. This comes because they approach in a angular fashion. This is the sigma bond, perfect sigma bond, when they approach in a coaxial fashion. This is the bond which is in between a pi and a sigma. Okay. And so, poor overlap, and that is why this is a weak bond. And the next what was suggested is that in order to strengthen the bond a little bit more, or in order to reduce the angle strain, so the hybridization, the internal orbitals, that means the orbitals which make the carbon-carbon bonds, the hybridization I already told you, it is about sp5. So, it has got 83% p character and 17% s character. Okay. So, that is the modern day concept of cyclopropane. Next, we come to cyclobutane. Now, in case of cyclobutane, Bayer considered it as a flat molecule. Okay. And flat molecule, and then the angle strain was calculated. I already in the earlier lecture, I told you about how to calculate the angle strain. It is 109.5 minus 90 divided by 2. However, later on it was observed, like I was telling, that these molecules, if you make it flat, they will suffer from not only from angle strain, but they will suffer from what is called the torsional strain or the eclipsing strain. This is the same thing, eclipsing strain. Some people call it Pitzer strain, because it is the scientist Pitzer who first introduced this concept of strain. So, this strain is called, when the bonds are eclipsed, they suffer from a strain, and that is called Pitzer strain. That is also called eclipsing strain, and today we generally call it torsional strain. So, they suffer from, when you make a flat system, the adjacent bonds will be eclipsing each other. So, it will suffer from the torsional strain. So, apart from angle strain that is present, it will suffer from torsional strain. The interesting point is, even if we reduce it to 0, the angle strain, like cyclopentane, it is almost 0, because it is 108 degree now, regular pentagon, and but you still suffer from this torsional strain, because these are eclipsing to each other. Okay. So, the question is whether it will now remain in this form or not, because it is suffering from torsional strain and it is suffering from angle strain. Now, the torsional strain you can reduce little bit if you make it not flat, if you make it little bit puckered. Puckered means non-planar. Then what will happen? See, if I try to move this carbon now a little bit, and this carbon, you see that the torsional strain, the bonds are no longer eclipsing each other. So, there will be slight dihedral angle it's not gauche yet, but the torsional strain will decrease as you move these two carbons upwards. But what happens if you move these carbons upward, the angle, these two angles now become less than 90, and if it becomes less than 90, so what increases is the angle strain. So, now you have a trade off. So, if you rotate it a little bit, if you make it little bit non-planar, then it will reduce the torsional strain, but on the other hand it will increase the angle strain. So, the question is which one it prefers. Okay. So, that will be in the next lecture.